Okay. So we are talking about partial fractions. Okay.
Yes.
Firstly, partial fraction involves some fraction by fraction. Okay. Something like this. Something by some polynomial by polynomial. Okay.
Hmm.
We're talking about something like the numerator is a polynomial, denominator is a polynomial. Okay. F of x is a polynomial, g of x is another polynomial. At the same time, this is a proper polynomial. What does that mean? The degree of f, that is highest power of f, is lesser than highest power of g. Okay. See here, the degree is 2 here. Here, if you multiply, it will become 3. Agree, Emma?
Yes.
Okay. So degree of f is lesser than degree of g. Okay. So first it has to be in proper fraction. If it is not in proper fraction, what we will do? We will just divide using synthetic division or long form division, whatever, to get into this format. Okay.
Okay.
You can always divide, right? You can always divide a polynomial by polynomial and simplify it, right? If it
Yes.
is not already in proper form. Okay. Now, let's assume it is already in proper form. Okay.
Hmm.
Then let us look at the denominator. This denominator g of x is there, right?
Okay.
Either because it is a polynomial, it can be broken down into multiple linear factors. I
Hmm.
mean, something like this. This is a linear factor, this is a linear factor, this is a linear factor. Okay.
Huh.
Or it cannot be broken down into linear factors. Okay. But in theory, any polynomial, let's say polynomial of order of degree n, so we'll have at max n roots, right?
Yes, sir.
So for example, if you can have a polynomial like x square minus 5x plus 6, it will have this parabola, it will have roots 2 and 3, x minus 2 into x minus 3. Okay.
Hmm.
But you can have a polynomial like x square plus 1. You cannot further break it down because it will have complex roots. X
Huh.
plus I times x minus I, right?
Yes, sir.
Okay, so this will have complex roots. Okay, but in theory, any polynomial, if it is of degree n, will have n roots, either real or complex, either repetitive or non-repetitive, etc. So, for example, x minus 1 whole cube. This is also a polynomial,
Hmm.
right? But it will have all three roots equal to 1. Okay, ma?
Hmm. Yes, sir.
Okay, so any polynomial, that's what we are saying. It will have at max n roots and real or complex, anything. Okay.
Hmm.
Now you already know the complex roots come in pairs.
Hmm.
Okay. Complex roots, they are actually conjugates. If 2 plus 3i is a root, 2 minus 3i is also another root, right?
Yes, sir.
Okay. So whenever you are getting complex roots, these two will combine together to get a quadratic equation, right?
Hmm.
Just like this. If you know x plus I is a root, x minus I is another root. So theoretically, they will combine to give an expression like this. Okay. So any polynomial, either you can break it into linear factors like this, or at least, if not linear, at least quadratic factors.
Hmm.
Okay. Linear into linear into quadratic into quadratic into linear like this. You can theoretically can always break.
Hmm.
Understood? So you don't need the cubic factors, because if you find a cubic one, any cubic equation will look something like this. It will touch x-axis at least once. Okay, it can touch 3 times for 3 real roots, but at least one real root should be there. Okay, any
Hmm.
cubic equation you can write it as one linear into one quadratic. Agreed, Emma?
Yes, sir.
Okay, similarly, any fifth power, any odd fifth power, you can write it as all 5 linears or linear quadratic, something like this. Okay.
Hmm.
If four roots are complex, one root has to be real, right? Why it
Hmm.
has to be real? Because it's an odd power. Odd power. F of minus infinity is minus infinity, plus infinity is plus infinity. It has to cross x-axis at some point. Okay. So
Yes.
any odd power will have at least one real root. Okay. Even
Hmm.
power, we cannot say that. Even power, so for example, x power 4, it can go up. X power 4 plus 1 or 4, it will go up like this. It will not have real roots. But then
Hmm.
also, because complex roots, they can come in they come in pairs. X power 4, you can still make it as quadratic into quadratic.
Hmm.
Understood?
Yes, sir.
So theoretically, what we are saying, any kind of polynomial, we can break into linears and quadratics. Okay. Now, theoretically, we are saying one more thing. These linears might be repetitive, quadratics might be repetitive. So, for example, you can get x minus 1 whole cube into x square plus 1 whole square, something like this. Or we can get x minus 1 into x minus 3 into something x square plus 4x plus 1, x square minus 7x plus 3, whatever. Okay, plus 7x plus 3, whatever. Okay, all linears could be different, all quadratics could be different. Okay. So essentially what we are saying any kind of polynomial we can always break into linears and quadratics, and at the same time linears can repeat, quadratics can repeat. This is what we are trying to say. Okay. Now let's say we have already broken. Okay, any polynomial is given, polynomial entire, we have already broken this into linears and quadratics. Okay. Now
Yes,
this
sir.
theorem says for every linear factor, okay, for every linear factor, let's say x linear factor is repeated m times. Okay, if a linear factor, same linear factor x minus r is repeated m times, then in the corresponding partial fractions we will get a term like this. So for example, if m is 1, then these all terms will not be there, only this one. Okay. Okay.
Understood.
Similarly, for every quadratic factor, if it is repeated n times, you will take the first one, second one, third one, up to n times. Okay. Similarly, if n is 1, you will get only one factor. Okay. These all
So,
will not be
so
there. Understood. So what we are trying to say, if a linear factor is repeated, we will take, if m times it is repeated, then we will take these m terms. First one, second one, third one, fourth one, fifth one. What is the difference? Here, first one you will not, you will take it to the power 1, second one to the power 2, third one to the power m, and mth one to the power m. Similarly, for quadratic equation, first one to the power 1, second one to the power 2, final one to the power n. At the same time, the numerator this time will be a linear function. If it is linear, this is numerator is plain constant. Okay, ma?
just one doubt.
Ah,
So for suppose for the first thing,
hmm,
if it is given as x minus 1
hmm.
cube, then
See,
three
ah,
times we will take it and
x minus 1
divide it.
cube. So x minus 1 cube. So numerator, this is a proper fraction. So you are saying you are given something like this. Okay? Or 2x square plus 3 by x minus 1 cube. Okay. Then what you will write this as a1 by x minus 1 plus a2 by x minus 1 whole square plus a3 by x minus 1 whole cube. That's it.
So here what is a1, a2, a3?
You have to find out. Theoretically, we are saying these are some coefficients. You will
Okay.
multiply this with this and this. You multiply this with this and this. Whatever. You take the LCM, right? You take the LCM, then what you will do? A1 into x minus 1 is already there, right? A1 into x minus 1 whole square. This becomes, right? Plus A2 into x minus 1, right?
Got it.
X minus 1 plus A3. This should be equal to 2x square, 2x square plus 3. Okay?
Understood.
Then you will
And then the
expand this and
same,
you will equate the coefficients and you will find out A1, A2, A3. Okay?
and then the
Okay.
same for p1x
Same,
plus c1,
same for
same.
anything. So, for example, take this example. Okay? Here there are three linear factors, all three are different. Okay? So, that's why we don't need, we'll stop at, uh, let me erase this. We'll stop at A1. Okay? We don't need these ones because the factors are not repeating. Okay? X minus 1, x minus x plus 1, x plus 3, all factors are non-repeating factors. That's why we'll stop here only.
So
So
what
for
if you have in denominator x plus 1?
x plus 1 is there, no? It doesn't matter. X minus 1 means,
No, no, not in this case.
in denominator x
And
plus 1 is there, no?
not this one, sir.
Tell me.
Just first case.
Hmm.
There, a by x minus 1, then a by x minus 1 whole square, like that. That one.
Ah, right, right. So you see, x minus r means this is positive, then I would have written as x minus of minus something. It doesn't matter
Okay,
actually.
doesn't matter. Okay.
Okay. So for example, in this case, if
Hmm.
if if you are got x plus 1 whole square, right?
Hmm.
Okay. 2x plus 3 by x plus 1 whole square. Then you would have written as a by x plus 1, x minus of minus 1, that is, plus, this is, let's say, a1, then a2 by x plus 1 whole square. That's it. Doesn't matter.
Understood.
Okay?
Understood.
Okay. Now what we have done, you multiplied a with this and this, okay? B with this and C with this and this, and you equated the respective coefficients with this. Okay?
Hmm.
You taken together x square, taken together x, and taken together constants, and compared the constants x square, this thing, whatever, and ultimately you solved for a, b, c. Okay? Here you found
So
out.
these are not considered as proper fraction, right, sir?
This is a proper fraction. Proper fraction, see, the highest power of numerator is x square. Highest the power of denominator is x cube, right? So this is
Hmm.
2 by 3. Okay?
So f of x, if it is less than g of x, proper fraction.
Proper fraction. But this has to be a polynomial. This also has to be a polynomial. You cannot put a square root in the numerator or denominator.
Okay,
Understood?
got it.
Okay. Powers, all powers should be integral powers. Okay?
Hmm.
Then only it's a, this applies for polynomials by polynomials. Okay, ma?
Okay.
Uh, so this you understood, no? Let's take another. Okay. Let's take some examples from our book. Okay. So these are called rational functions. What are the rational functions? Polynomial by polynomial. Okay, ma?
Hmm.
So in this case, we have done this. Okay. Now look at here. Here, linear factor repeating twice. Okay, ma?
Yes, sir.
Linear factor repeating this. So what we will write this as a by x plus 2 plus b by x plus 2 whole square. Okay, ma?
Yes,
Then
ma'am.
here a into x plus 2, b into x plus b into anyway 1 because x plus 2 whole square. So this is LCM is x plus 2 whole square only. Okay. You are
Hmm.
comparing this, and you are getting a and b, and you are directly integrating. Okay.
Hmm.
This because this is in linear, it becomes very easy, right? You can substitute x plus 2 as t, then 5 by t square, which is t power minus 2, t power minus 1 by minus 1. Okay, ma?
Yes, ma'am.
Okay. See here. This is not a proper fraction, right?
Yes, sir.
Because this is cube, this is square. What you do? You divide numerator with denominator. You know how to divide, right? If you
Yes, sir.
divide, you are getting this remainder. So you are writing this as this, whatever is this plus this by this. Agreed? You can write it, no?
Hmm. Yes, sir.
Essentially, what we are saying, this times plus this is equal to this. Okay. 2 into this one plus remainder is actually equal to this. Okay. 2 into this one plus remainder is actually equal to this. That's what we are saying here. Okay. We are just dividing this one with this to find out what is this and this. So this is a proper fraction now. This anyway you know how to integrate. This is very easy integration, and this is a proper fraction. Now can we break x square minus 2x minus 3 into two linear factors? Yes, we can. X plus 1
Hmm.
into x minus 3. So that's why we're doing a by x minus a by 1 factor, b by 1 factor. Okay, linear. That's why two simple steps. Okay.
Yes, sir.
See here, x square plus 1 you cannot break it further. Agreed?
Hmm.
Okay, because this is already complex roots. And x
Hmm.
minus 1, there is a repeated linear factor. So what we will do, for x minus 1, you will get two terms. 1, 2. Okay, x minus 1 whole square. For this one, you will take only one term. What is that term? Ax plus b by x square plus 1, right?
Yes, sir.
You remember that, no? So for
Hmm.
this one, because you cannot reduce into linear factors, we will write it like this. Okay, ma?
Yes, sir.
Okay. Next, then again you are equating coefficients and you are simplifying A, B, C, D. This sometimes it becomes lengthy. That equating coefficients and simplifying. Okay. Okay, but the process is simple.
Okay,
Now
sir.
see here. Here what you will do? This factor, this quadratic factor is repeating. Okay, like this. So we will
Hmm.
get these two terms, first and second, right?
Yes, sir.
And for x, you will get one term. Okay, for x one term. for x square plus 1, 1 dx plus c by this thing, and 1 dx plus c squared. Okay? Again, you will equate coefficients. So basically, you have a, b, c, d, e. 5 equations, 5 unknowns you should get, and then you will solve for everything. You got this one. Okay, ma?
Yes, sir.
Okay. And rest all, once you reach here, so this is very easy, right? We did this in the past, right?
Huh.
These kind of things. Okay?
Okay.
This is easy actually. Use x square plus 1, you substitute as u, and 2x dx will become dt. Whatever. You can easily do. Okay?
Yes, sir.
Okay. Now, sometimes this kind of writing equations and then solving for 5 different equations will become little tedious. Okay. So, there is a special method, but this applies only for when you can break everything down to linear factors. Okay.
Mm. Yes, sir.
Okay. Denominator, you are already broken down to linear factors. Then what are the coefficients? Okay. So for example, this case only. Denominator is already broken down to linear factors. Okay.
Mm.
So we know there will be only 3 coefficients. Okay.
Yes, sir.
Denominator linear factors and non-repeating linear factors. Please remember this. This Heaviside method. Okay.
Mm.
Denominator non-repeating linear factors. All linear factors are different. Okay.
Mm.
Understood?
Yes, sir.
Then what we do, let's we to calculate a, what we will do when x equals to 1, we evaluate x minus 2 into x minus 3. Okay,
Mm.
so basically what he's saying, he's saying um, this can be broken down into these factors, right?
Mm. Yes, sir.
Then if we multiply x minus 1 on both sides, what will happen? We'll be left with a plus b by this thing, x minus 1 by x minus 2, plus c by this thing. Okay.
Mm.
Okay. Now, because if you substitute x equals to 1, what will happen? These two will become 0. Okay.
Oh.
These two will become 0 na? X minus 1 is there. So what is out here? Basically, you substitute x equals to 1 in this equation by removing this one. Okay. So
Mm.
basically, what you are saying, to get a, what you are doing, when you are substituting x equals to 1 by covering the corresponding s factor. Okay. Cover up
Yes.
method. Okay. You are covering x minus 1. So they basically assume it is not there and evaluate this value. Okay.
Same, we can do the rest two terms also,
Rest two
no?
terms also. This time what you will cover? You will cover this one. Okay.
X minus
We will assume it
mm.
is not there. So and what is the value at which you will evaluate? You will evaluate at 2. 2 square
2.
plus 1 by 2 minus 1 into 2 minus 3. Okay.
Mm.
Similarly, you will cover x minus 3 and evaluate this function at 3.
3.
Okay. So then you will get the value of c. Okay, ma?
Got it.
So for example, he is covering this one and evaluating remaining function at x equals to 1. Okay. He is covering this one and evaluating remaining function at x equals to 2. Okay. But this will work brilliantly when all linear factors are different. Okay. And
Yes.
and needless to say, it is all proper fractions only. Okay.
Yes.
Okay. Understood, no? This is the Heaviside cover up method. This actually helps a lot. Okay.
Okay, sir.
Okay. So probably your complex factors, these kind of cases, your can you see my mouse?
Mm. Yes, sir.
Where I can't see it moving. I don't know. Can you see the mouse moving?
Yes, sir, I can see it.
But I can't see. I think somewhere it is stuck. I can't see where is my mouse. Let me just rejoin, or I think I
Okay.
have to restart my system. Okay, give me 5 minutes.
Sir, you text me, then I'll join the class again.
No, no, just wait. It is just my this thing doesn't take a lot of time. You stay
Oh,
on the line only.